So, I want you to picture a student taking a final exam, and let's call him Bert.
Okay, Bart.
Yeah. Bart is, he's brilliant. He has memorized thousands of textbooks. He can quote Shakespeare. He can explain quantum mechanics, tell you the population of Peru. But there is a pretty massive catch.
He's been locked in a room.
Exactly. Locked in a room for 2 years. He has no internet connection, no new books, zero updates. So if the population of Peru changed yesterday, Bart doesn't know.
Right.
If a new president was elected, Bart is blissfully unaware of it. And the worst part of all this, when he doesn't know the answer, he is so confident in his own brilliance that he just makes something up that sounds right.
Which is the classic hallucination problem. It is basically the Achilles heel of what we call parametric memory.
Right. So now I want you to imagine a second student, and we'll call him Rag.
I see what you're doing there.
I try. So Rag, he might not have memorized nearly as much as Bart. In fact, his internal memory is significantly smaller. But Rag is allowed to bring a massive up-to-date encyclopedia into the exam room.
The open book approach.
Exactly. And not just bring it in, but he can look things up for every single question before he writes a single word. So who passes the test?
Rag wins. Hands down, Rag wins. And it doesn't just pass. He gives you his citations.
And that is the core of the source material we are doing a deep dive into today. We're looking at a paper titled Retrieval Augmented Generation for Knowledge-Intensive NLP Tasks,
by Patrick Lewis and the team at Facebook AI Research, University College London, and NYU.
Right. And for anyone listening who uses AI today, this paper is essentially the reason we stopped trying to cram the entire internet into a model's weights and started teaching models how to use a library instead.
It was a fundamental architectural shift. We really moved from those closed book exams to open book exams. But you know what's fascinating about this paper isn't just the concept itself, it is the execution.
Yeah, they didn't just glue a search engine to a chatbot.
No, they made the retrieval process differentiable, which is huge.
And I think that's exactly where we need to start because I think a lot of people just assume RA is Google search plus a language model.
Right, like a script scraping results.
Yeah, like you type a query, some script scrapes the top 3 results, pastes them into the prompt, and just says, hey, summarize this. But that is absolutely not what Lewis and his team build here.
No, that would be a heuristic approach. And heuristics are brittle. What Lewis proposed in this paper is an end-to-end learned system. They actually treat the retrieved documents not as hard text inputs, but as latent variables.
Okay, let's unpack the gears of that a little bit. We have 2 main components in this architecture. We have the retriever and we have the generator.
Right.
Now, the generator is pretty standard. It's BART, which is a sequence-to-sequence transformer model. We know how that works. But the retriever is different. They're using something called DPR, or dense passage retriever.
Yes.
How is DPR actually different from an old-school keyword search, like BM25 or something you'd use in Lucene?
The main difference comes down to vector space. Traditional search is just matching keywords.
Yeah.
If you search the word feline, it strictly looks for the word feline.
Or maybe cat if it has a synonym list.
Sure, but it's limited. DPR uses a bioencoder architecture that's based on BERT. So it takes your question and it encodes it into a dense vector. And then it has already encoded every single document in Wikipedia into its own dense vector.
So it's essentially mapping the meaning of the words, not just the strings of characters themselves.
Exactly. It maps all of them into this shared latent space. And then to actually find the relevant documents, it performs what's called a maximum inner product search, or MEMI-FEAS.
Which sounds very complicated.
It just means it's calculating the dot product between your question vector and millions of Wikipedia document vectors to find the ones that align mathematically.
Okay, but that sounds incredibly computationally heavy. If I'm asking a chatbot a question, I do not want to sit there waiting for the model to do a million dot products.
And that is exactly why they use FEAS. It's Facebook's library for efficient similarity search. It indexes all those vectors beforehand. So the lookup process is sublinear. It is incredibly fast in practice. But honestly, the really critical part that distinguishes this 2020 paper from everything else
is the joint training.
Yes. The retriever and the generator are trained jointly.
And this is the part that I think always trips people up, because how do you even train a retriever? Usually for machine learning, you need labeled data. You'd need a data set that says, for this specific question, this specific Wikipedia article is the correct document.
Right, you'd need explicit supervision.
But they didn't have that for every query they were training on, did they?
No, they didn't. And that is the sheer beauty of this architecture. They didn't need explicit supervision for the retrieval step. Because they treated the retrieved document as a latent variable, The signal to update the retriever actually comes from the generator.
Walk me through exactly how that works. Let's say I ask a question.
Okay, so you ask a question, and the model retrieves a document. Then the generator tries to answer your question using that specific document.
Okay.
If the generator's answer is correct, meaning it actually matches the gold standard target text in the training data, the loss is very low. So we backpropagate that gradient.
Meaning the math flows backwards through the network to update it.
Exactly. That gradient tells the generator, hey, good job, but it also flows all the way back to the retriever. It effectively tells the retriever, that document you gave me was really useful. Keep finding vectors that look like that.
So the retriever learns what a useful document looks like purely based on whether or not the generator could write a good final answer with it.
Precisely. It basically learns to be a better research assistant, not by someone explicitly telling it which books to pick off the shelf, but just by seeing if the writer gets an A on the final essay.
That is extremely clever. It completely sidesteps the need for these massive hand-annotated data sets of question and document pairs.
It really does. But the paper doesn't just stop at, hey, we built this cool system.
Yeah.
They actually propose two entirely different ways to use those retrieved documents during the generation phase. They call them arg sequence and arg token.
And this is where the math gets really interesting. Because RSD sequence feels like the much more intuitive approach to me. You retrieve the top K documents, let's say the top 5 documents, and then you generate an answer for each of those documents independently, and then you marginalize.
Right. You're essentially asking the model to pretend. You say, assuming document A is the absolute truth, what is the answer? And then you say, assuming document B is the truth, what is the answer?
So you end up with 5 different fully formed answers.
Yes. And then you look at the probability of each complete answer sequence.
So it just picks the one answer that it is the most confident in.
Effectively, yes. It sums the probabilities. Technically speaking, it is approximating the probability of the sequence Y given the input X by summing over the latent document Z.
So it's kind of like a mixture of experts approach.
Exactly. The documents vote on the final output, but the output text itself comes from a single lane, a single document.
Okay, so to make that concrete, if document A is all about the history of Peru and document B is all about the geography of Peru, arg sequence is going to write a purely historical answer or a purely geographical answer. It commits to one lane.
Correct. It stays in its lane. But arg-air token, on the other hand, arg token is the Frankenstein monster approach. It breaks the lane discipline entirely.
The Frankenstein approach. Explain how this works, because when I first read this part of the paper, it seemed like it should just result in total gibberish.
In arg-a token, the model still retrieves the exact same top K documents. But instead of committing to one single document for the whole answer, it marginalizes the probability distribution for every single token it generates.
Token by token. So for the first word of the sentence, it looks at all 5 documents, and then for the second word, it looks at all 5 documents again.
Yes. If you think about the math happening under the hood, for the next word, it sums the probability of that word given document A, plus the probability given document B, and so on. It aggregates the knowledge of all the retrieved documents simultaneously to choose just the next single word.
That honestly sounds chaotic. If I am writing a sentence right now, I can't switch my source material every time I write a single word. I would completely lose the thread of the sentence. How does the model keep the grammar coherent?
Well, that is the magic of the underlying transformer, the BART model. The generator still has its own internal state. It has its own parametric memory of grammar and syntax and structure. It knows perfectly well how to write a fluent sentence.
Oh, I see. So it's just swapping the facts it's injecting.
Right. Our token just allows it to inject facts from different sources exactly as needed. If document A has a specific date and document B has a specific location, our token can literally pull the date from A and the location from B inside the exact same sentence.
But does it actually work like that in practice, or is that just a nice theoretical idea?
Oh, they proved it works. And the specific example they provided in the paper is easily one of my favorite parts of this entire deep dive. It's the Hemingway experiment.
I loved this part because they tasked the model with generating Jeopardy questions, which is fundamentally harder than answering them, because generating a clue means you have to be highly specific and factually precise.
Exactly. So the target entity they wanted the model to generate a clue for was Ernest Hemingway. And the RE token model successfully generated this exact clue. The Sun Also Rises is a novel by this author of A Farewell to Arms.
Okay, so that is 2 very distinct facts, 2 completely different books in one sentence.
Yes, and the researchers visualized the attention weights during the generation of that sentence. Basically, they were looking at which specific document the model was focusing its attention on for every single word.
And what did they find?
When it generated the words, "the sun also rises," the model was attending almost exclusively to document 2, because document 2 specifically mentioned that book.
And then what happened when I got to the second half of the sentence?
As soon as it hit the word "a" in a farewell to arms, the attention weight swung wildly over to document 1, which was the document that discussed his war experiences and that specific novel. It literally performed a massive context switch mid-sentence.
It hot swapped the source material right in the middle of a thought.
Exactly. And RAG sequence could never do that. RAG sequence would have been stuck trying to find one single Wikipedia page that contained both of those facts in close proximity.
And if no single document had both facts, it probably would have just failed or hallucinated something.
Right. But RAG token synthesized a brand new fact by stitching together two partial truths from different places.
That distinction between sequence and token is something I really think gets lost in all the current hype around RAG. RAG token implies a level of synthesis that goes way beyond just reading a document. It is actively integrating information.
It creates a model that is arguably much more robust to incomplete data. You don't need to find the one perfect document anymore. You just need a collection of documents that collectively cover all the pieces of the answer you need.
Well, let's talk about the actual results, because all of this fancy architecture means absolutely nothing if it doesn't beat the benchmarks.
True.
They compared this RAG architecture against T511B. Now, for some context for you listening, T511B is a behemoth of a model.
It is massive. 11 billion parameters. And it's a closed book model, meaning it relies entirely on what it managed to memorize during its incredibly expensive training run.
Right.
The RAG models they used for this paper were significantly smaller in terms of parameters. They used BART large as the base, which is only around 400 million parameters.
So RAG is roughly 4% the size of T5.
In terms of neural weights, yes.
Yeah.
But RAG obviously has the external index to pull from. And despite being a fraction of the size, RAG set the new state-of-the-art performance on open domain question answering tasks. Data sets like Natural Questions, Trivia QA, and WebQuestions.
So it actually beat the giant.
It beat the giant handily. And it did so while generating answers that were far more specific. There is a metric they used for that Jeopardy question generation task we just touched on. They brought in human evaluators and found that RAG was more factual in 42.7% of cases.
Wow. And what was the baseline?
Standard BART was only more factual in 7.1% of cases.
That is not just a margin of error improvement. That is a complete paradigm shift in accuracy.
It really is. And that brings us to the FEVER dataset, which I actually consider the sleeper hit of this entire paper. FEVER stands for fact extraction and verification. You feed the model a claim, and it has to classify if that claim is supported, refuted, or if there's not enough info.
But usually that requires a complex pipeline, right? Like you have to build one system to go find the evidence, then a separate system to read the evidence, and a third system to classify it.
Correct. It's normally highly engineered and very supervised. But our RAG took a completely different approach here. They just gave the model the claim and the final label. They didn't tell it which evidence to go look for. They didn't supervise the retrieval process at all.
So the model had to figure out entirely on its own that to prove this claim about the Roman Empire, I need to go search for a document about the Roman Empire.
Yes. And it achieved results that were within 4.3% of those highly complex, specialized pipeline models. It learned to be a fact checker just by trying to minimize the error on the final true or false label.
Which suggests that RAG isn't just a trick for Q&A chatbots. It is a general-purpose architecture for any NLP task that requires evidence.
Exactly.
But there is a phrase you used earlier that I want to drill down on. You mentioned parametric versus non-parametric memory. We defined them at the start, but the real-world implications of splitting them apart like this are huge, specifically when it comes to the ability to update a model's knowledge.
Ah, yes. The hot swap.
The hot swap. Because in a traditional parametric model, if I want to teach it about a new event, say COVID-19, and the model was trained back in 2018, I have to retrain the whole thing from scratch. That costs millions of dollars and takes weeks of compute.
Or you try to fine-tune it on the new data, which very often leads to catastrophic forgetting. That's where it learns the new stuff but completely overwrites or forgets the old stuff.
So what did Lewis and the research team do to test this with RAG?
They ran a really beautiful experiment. They took the RVAG model that they had trained using a December 2018 Wikipedia index, and they asked it a simple question. Who is the president of Peru?
Okay.
The model answered Martin Vizcarra, who was indeed the president in 2018.
So the answer is correct for the time period of its library.
Right. Then, without touching a single weight inside the neural network, no retraining, no fine-tuning, no backpropagation at all, they simply deleted the 2018 Wikipedia index and plugged in a 2016 Wikipedia index.
So they just swapped the hard drive, essentially.
Effectively, yes. Then they asked the exact same model, the exact same question, and the model immediately answered, Pedro Pablo Kuczynski, who was the 2016 president.
That is basically a Matrix moment. Like, I know Kung Fu. You literally just load a new cartridge into the machine.
It fundamentally decouples reasoning from knowledge. The neural network, the BART component, is purely the reasoning engine. It knows how to answer questions, how to structure its sentences, how to synthesize the information, but the index is the knowledge base. And you can swap the knowledge base instantly without breaking the reasoning engine.
And this completely solves the enterprise problem. If I am running a bank and my interest rates change this morning, I absolutely do not want to retrain my AI. I just want to update the PDF in the corporate folder and have the AI know the new rates immediately.
Exactly. It makes AI dynamic instead of static.
Yeah.
But it also introduces a really fascinating philosophical question about what learning actually means for an AI. Well, in the past, learning meant encoding facts directly into the synaptic weights of the network. But now, learning might just mean learning how to search better.
I want to push back on that just a bit, though. If the model is strictly only as good as its external index, doesn't that just shift the point of failure? Because if I feed it a corrupted index or a highly biased Wikipedia dump, the model is going to confidently output garbage.
Absolutely. And the paper is very clear and transparent on this limitation. RJ is faithful to its sources. If you index a conspiracy theory blog, RJ will generate incredibly convincing, well-cited conspiracy theories. It is not an absolute truth machine. It is a retrieval machine.
Which means curation is more important than ever.
Yes.
And there's also the ongoing issue of interpretability. One of the big knocks on deep learning generally is that it's a black box. We don't really know why a massive model said what it said. Does R actually fix that problem?
To a very large degree, yes. It doesn't solve the black box of the neural network itself, but it gives us an audit trail for the facts. We can see exactly which documents were retrieved and attended to. If the model says the sky is green and we check the logs and see it retrieved a document called Sci-Fi Novel About Mars, we know exactly why it made that mistake.
So we can debug the knowledge itself.
We can debug the knowledge and we can actively curate it. We can block certain malicious documents. We can prioritize trusted medical sources over Reddit posts. You cannot do that with a standard language model. You can't just reach in and manually surgery out a specific neuron that holds a specific misconception.
That makes a lot of sense. Now, you mentioned earlier that RAG is computationally efficient in terms of its parameter count being small. But isn't running a dense retrieval step for every single query, or worse, for every single token in RAG token, isn't that much slower than just doing a single forward pass in a static network?
That is the primary trade-off. RAG is slower at inference time than a pure parametric model like standard BART. You have the overhead of the retrieval step, the cross-attention mechanisms, the marginalization math. It's certainly not free.
So it becomes the trade-off between fast and static versus slightly slower but highly accurate and updatable.
Generally, yes. Though slower is a relative term here. With optimized indices like Facia, it is still completely viable for real-time chatbot applications. But you probably wouldn't use RAG token for something like a high-speed autocomplete on your smartphone keyboard. It's just too heavy for that.
I want to circle back to the training aspect one last time before we wrap up. You mentioned the retriever is trained by the generator's gradient signal, but what about the generator? Does the generator's behavior change during this joint training?
Yes, both components are updated simultaneously. It is a cooperative game. The generator actually has to learn to utilize the noisy, imperfect documents provided by the retriever. Because at the very beginning of training, the retriever is terrible. It is just grabbing totally random documents. So the generator has to learn to ignore the garbage text.
Right.
But as training progresses, the retriever gets much better at finding the gold, and the generator gets much better at extracting and refining that gold into a coherent answer.
It's kind of like a new executive and a new research assistant starting at a company on the exact same day.
That's a great analogy.
Right. At first, they're both bad at their jobs. The assistant brings the wrong files, and the executive writes terrible reports. But over time, the executive shouts, "Hey, bring me files about physics, not physiques." And the assistant adjusts.
And simultaneously, the executive learns that even if the assistant brings a slightly irrelevant file, there might still be one really good data point buried in paragraph 3. They co-evolve.
That coevolution is really what makes this paper such a landmark. It's not just clever software engineering, it's an entirely new way of training a specific capability into a model.
It really is. And if we look at where we are now, a few years post-paper, RAG has absolutely become the default architecture for enterprise AI. We aren't just trying to build bigger and bigger static models for vertical tasks anymore. Everyone is building RAG systems.
Which brings us back to those philosophical implications. If we can hot swap knowledge on the fly, and if the actual brain of the AI is just a reasoning engine, are we approaching a practical limit on how big that brain actually needs to be?
That is the trillion-dollar question in the industry right now. The trend for an entire decade was scale is all you need. Yeah. Bigger parameters, more training data. But RAG suggests that maybe context is all you need. If I have perfect retrieval from a perfect library, maybe I only need a relatively small, highly efficient reasoning engine to process it.
It fundamentally changes the definition of what an expert is. An expert isn't someone who has memorized everything. An expert is just someone who knows exactly where to find the information and how to synthesize it accurately.
Which, ironically, is exactly what we teach human beings in the modern internet age. We don't force students to memorize the encyclopedia anymore. We teach them research skills. We are finally building AI in our own modern image.
We are finally building AI in our own modern image. That is a really powerful thought to land on. It suggests the future of artificial intelligence isn't some isolated superbrain in a jar, but a highly connected researcher with an infinite library card.
And hopefully a researcher that clearly cites its sources.
One can certainly hope. And that makes you wonder, if you could hot swap your own personal memory with a specialized index for a single day, which one would you choose? Imagine suddenly becoming an expert in astrophysics or 14th century architecture just by loading a file into your brain.
I would definitely take the astrophysics index.
Yes.
Although I would probably hallucinate a lot less if I stuck to the architecture one.
A very fair point. We will leave you with that thought to mull over. The line between knowing something and finding something is rapidly disappearing, both for machines and for us. Keep your libraries updated.